Hello everyone, this is Dr. Rachita Misra speaking to you. Today in our course of software engineering, we will be discussing on the principles of software design. In the previous lessons, we have looked into the requirement analysis activities. And inside that requirement analysis activities, we have seen the elaboration, and we have created so many analysis models. Now we will come to the design part, which is the next major activity in our software engineering activities. This is after engineering discipline. This is a major activity where we are modeling the technical aspects of the software so that it can move to the construction or the coding of the programs which will be comprising of the software. So today we will cover topics such as we will look into what is design engineering, and in the context of software engineering, how we can apply design engineering. Then we'll look into the components of the software design, and we will see how they are mapping to the analysis models which we discussed in the previous class. And then we will look into the software quality attributes, and from the software quality attributes we will try to create some design principles or guidelines for quality software. And then we will look into some of the very important concepts in the software design area. So what is design engineering? So design is not only done in the software, but it is done for any product, any engineering product, whether be it mechanical of nature or electrical or whatever, maybe even the house construction, which is civil, or a bridge construction. They all require any engineering activity which involves product or service. They require a design. So design engineering covers the set of principles, concepts, practices that lead to the development of a high quality system or product. So not only that there are some principles, but there are some concepts or some certain terminology and certain knowledge area that we use in it, that is the concepts. Also how we practice it, what is the how it is, what are the methods of practicing it. So over experiences, how it is matured. That these all things together are termed as design engineering. And what is the output of that? So its goal is to develop a high quality system or a product. So and also it is when it says it is a product, then it should be able to produce models or representations that depict certain values. So in the design engineering, what we try to do, instead of before creating the actual product, we are trying to model it or create a representation of the product in the form of models which will have certain intrinsic value of the product. The one is firmness, which is basically accuracy, reliability, stability, things like that. Then the commodity value. Commodity value means it should be suitable to user and it can be used by many users. So it can be used as a commodity. It can be bought as a product, and there should be some delight value. That means the customer should feel very happy to use it. So the usability should be very high. The friendliness should be good. Next, when we draw these things into the software, we see that we will similarly have to create software design models, just like other engineering disciplines are creating models to represent the product with certain values. So also we will have to create in the software product development. We also have to create software design models. And what are these? These provide us details about the software data structures, architecture, interfaces, and the components. And these all together are necessary to implement the system. So whatever is necessary to implement the system, all those things become our design components. So accordingly, the software design will consist of four major activities: data class design, data or class design, and or it can be both also, because the database is also involved and class is also involved, and architectural design, that means how it will be organized, and the interface design, which is the user interface, the interactions with the user or any external party, and the component design, that means how the components will be defined in the software. So let's take a little bit more look at each one of this. A data or class design, this is actually coming from the class-based elements. In the analysis models, we have the class-based elements. That is your class diagrams and the data flow. And these are transformed, or are the data structures. And these are transformed into classes and data structures required to implement the software. That means we already have analysis classes, and now we are going to extend it. We are going to refine it to the design classes. And similarly, the data structures will also have to be, and the data relation will also have to be refined for the design part. Then we have to come to the architectural design. In the architectural design, it will define the relationship among the major structural elements of the software. This we can get from the class-based and the flow-oriented elements. So when we check these two analysis models, then from there we can try to understand the nature of the software and its use, and then we can define its architectural design. Then we come to the interface design. It shows how the software and the related hardware and the end user, how do they communicate with one another when they are performing a required function. So these can be derived from the scenario-based, flow-oriented and behavioral elements of the analysis model. And then finally, we have the component level design or the module level design. This is a refinement of the architecture. So in the architecture, we have given the overall organization of the software components. Now we will partition it further, refine it further to create smaller structural elements, which is normally called modules or components. And then we will convert its procedural descriptions of the software. So along with the structure, we will also have to write the procedural descriptions of the software components. And these we will do by using the three types of elements analysis model, that is class-based elements, flow-oriented elements, and behavioral models. So these analysis models or diagrams we will utilize to create the component level design in the designing activity. So this diagram is showing you how it is related. It's a mapping. So we have this flow-oriented elements, behavior elements, class elements, and scenario-based elements, and these are the different models. As we have seen in our previous lessons, we have gone detailed into how to create these models. And now, as you can see, these arrows are indicating how they are related. For example, for the data class design, we will be taking the class-based elements, and from here we will be creating the data and the class. And for the interface design, we will be taking the scenario based, that is from the use case we will get what is being done. From the activity diagram we will get the operational flow, and from the state diagram and sequence diagram we will also get to know the objects that are interacting and the messages. And from the flow oriented we will get the control flow. So those data flow and control flow we will get, and these three together we will try to do the interface design, and like that for all the four. So you can see this is like a pyramid. So this is a base, class data and class design, and we keep building over it. So because we said that component design is an extension of the architecture design. So we do it in this sequence so that we try to come to the lower level of abstraction, which is the module. So what is the importance of good design? Why should we try to do the design? Can we eliminate it? So design serves as the foundation for all software development and maintenance activities that follow. Just as requirement engineering created the foundation for design and construction, so design creates the foundation for construction. Being the step that will accurately translate the customer's requirements to the delivered software, quality has the main focus of design activities. So this is translating the requirement, which was more on the business language, to a technical language, so that it can be converted into the actual delivered software. And during this time, because we are translating it, we have to we have to understand that the focus has to be on the quality of the final deliverable, and therefore design activities have to be under quality control. Then design process is an iterative method, so it is not done in a single go. We keep refining it, and finally we create a blueprint for the construction of the software. So the characteristics of the good design, and that can be taken as the goal of the design process. So what are the things that we have to take care to get the good design? So must implement all stated requirements in the analysis model as well as all the implied requirements. So when we create the good design, it must take care of all the stated requirements, which are mostly functional requirements, and also some of the implied requirements. We have seen in the previous class that there are stated requirements, implied requirements, and something which creates delight to the user. So there's two major requirements which are stated and implied, all have to be designed into some of the design models. Should be readable and understandable to guide the development of the code or the testing of the software, and also for the subsequent maintenance support. The design should address the functional, data, and behavioral aspect of the intended software. So the design models that we will create, that should embody all these things. It should have a functional aspect, and it should address the data aspect, it should address the behavioral aspect of the intended software, whatever is the software that we want to deliver to the customer, that we are designing. So when we design it, we have to consider all these three aspects. Now we have talked of the design, good design. Now let's look at the quality attributes of our product, which is the software. So normally we consider the software quality attributes. The product must have certain attributes, or it is also called as the product characteristics. So later on, when we discuss about metrics and testing, we will deal more with product characteristics. So currently, let us call it as software quality attributes, or the property of the software which will ensure the quality. So when we say a software is of high quality or good quality, when it has these characteristics. The first one is the functionality. That means the stated and the implied requirements. Those things, whatever are the functions and the features in it, those should be delivered. The software should comply to those requirements. And usability, that means the software should be easy to use and also learn by the user. It should be aesthetic. Its look and feel should be aesthetic, and it should be consistent. That means whatever notations we use in the external appearance of the software should be consistent, so that it will be easy to understand, and should be well documented for the operation of the software in the long run. Then the performance parameters, there are certain performance parameters. Those things should be of high nature. That means these are normally measured by different parameters. Some of it is like response time and resource consumption, throughput, and different types of efficiency. There are many more. performance characteristics. I have just stated a few to be able to understand. But whatever is the performance that is required from that particular intended software, intended product, that has to be delivered. Then there is a set of supportability features. The supportability feature, or rather maintainability features, these include the capability of extensibility. That means it should be written in such a way that when we want to add features, we want to extend the software with additional features, it should be easy for us. Adaptability, that means it should be able to adapt to the environment. That environment could be some kind of soft operating system, or it could be any other utilities, things like that. So it should be able to adapt. And it should be serviceability, required for proper maintenance of the software. So all these things are basically certain parameters or characteristics which we need for the good maintenance of the software. It also includes additional abilities such as testability, compatibility, configurability, portability. Compatibility means in different environments. So configurability means we should be able to configure it. It is not fixed, so that when we change the environment, we can configure it. So like that, when we go to the product characteristics, again we will look into it. But basically, there are these four types of quality characteristics, four classes of quality characteristics or quality attributes that we expect from good software. So our design principles should be based on the quality of the software that is expected. So this we can call it as the design principles. There are 8 principles, and this we can also call it as we can take it as guidelines for the design quality. Because if the design quality is good, then only we can get the good quality software. So let's look at those. A design should exhibit an architecture that is created using standard architectural styles or patterns. So there are many architectural styles and patterns that are available, which has been used, which has been developed by people, and it has been tested and found to give good results. And there are many tools and software environments which are developed across those architecture. So whenever we make a design, we should try to use these known architectural styles and patterns. And it should be composed of components having good design characteristics. We have seen what were the design characteristics. And it should be implementable in an evolutionary fashion. That means we don't have to do everything together. We should be able to do it little by little. That means the design should unfold in such a way, it should be written in such a way that the implementation or the development or the construction can be in an evolutionary fashion. Basically, if you have partitioning and modularity, which we will read subsequently, we will see that it can become evolutionary. And so also you might be remembering that we have created these evolutionary models for the software process. So if the design is made in that way, then it is easier for us to follow some of the evolutionary process models and also the agile models. So that is why this is a good design practice principle or a guideline for the design quality. Similarly, design should be modular, that is, software should be partitioned into logically and smaller elements or subsystems so that we can have components. And there should be distinct representation of data, architecture, and interface and components. So these 4 parts of the design should be separately represented, distinctly represented. A design should lead to data structures drawn from recognizable data patterns. So we know so many data patterns we have read in our data structure classes. So we should not do something new all the time. We should only try to do some of the recognizable thing, and we may extend it. And also, if we do that, then it will be very appropriate for our implementation in classes or in program modules. Then we come to the next one. I think it should be 5, 6, 7, 8. Numbering is slightly different. Never mind, there are 8 principles. We have completed 4, and so there are 4 here. Design should be able to create components that provide independent functional characteristics. So these components or the module should be having that kind of functional characteristics which will be independent of each other, so that it can be executed on its own. It doesn't have to depend on other modules as much as possible. A design should be able to create interfaces that provide simpler connections between the components and its external environment. So whenever a module or a design component has to interact, then there should be some very simple interface or connection which can be established, and so that the interaction will be easy. Its interaction will be simple and efficient. So that external environment could be anything outside that particular module. A design should be derived using a repeatable method that is driven by information obtained during software requirement analysis. So the design process should follow that manner, so that when whatever we do in the design, we can do it repeatedly for other designs also. So whenever we are designing, whatever we are designing for one software, whatever we are doing to convert requirement analysis to design, the same thing we should be able to repeat. That means we should follow certain standard methods and process during the designing, so that it can be repeated for other software projects. And design representation should use notations that effectively communicate its meaning. So we should be careful about the notations that we use in our design models, so that the communication will not be confusing, it will be consistent, and also it will be effective. Now we will go into some of the design concepts, because we will continuously talk of these concepts throughout the design lessons. So some of the concepts are used for designing quality software, which have evolved over years of software engineering practice. They still stand good, though the software engineering methodologies and processes have changed over time. So these are some of the basic concepts. Of course, new concepts are coming on. So this is not exhaustive, but they are some of the basic concepts which are used in creating more and more emerging concepts. So they are abstraction, refinement, architecture, patterns, modularity, information hiding, functional independence, and finally refactoring. So we have already talked of some of these things in this class or in previous classes somewhere. So I'm sure they are not new terms to you, but we will try to understand what these are in context to good software design. So design concepts provide the necessary framework to get the things on the right way, or you can say do the things right from the first. That means when you start it in the right way. So let's look at what it means. What is the description of these concepts? So the first one was abstraction. When we do the abstraction, abstraction says that means we try to hide things. We try to give a high level description. We don't provide all the details. So that is called abstraction. Abstraction means hiding of details. So it should start at the highest level of abstraction. That means we have to start a solution in a very broad way, and then slowly provide more details at a lower levels of abstraction. So we should have hierarchy of abstractions. Higher level, which will be very high level of abstraction, and then there should be lower levels of abstraction. Two types of abstractions are provided when we do the designing. There are two types of abstraction that we can provide. One is the procedural abstractions, and the other is the data abstraction. In the procedural abstraction, the sequence of instructions that have a specific and limited function, those things are being done. That means we define a function at a higher level and then at a lower level and then at an even lower level. So that is what is the abstraction for procedures, which is applicable to the functions. And then we have data abstractions, which is the collection of data that describes the data object. So even when we do the data when we do the data structures or data objects or classes, that time also we have to do the abstraction of higher level to lower level. Then comes the concept of refinement. So refinement is a top-down approach to design proposed by Nicholas, and it begins with a statement of function or information defined at a higher level of abstraction. The statement describes function or information conceptually but provides no information about the internal working and or the internal structure. And as and when the refinement occurs, we keep on elaborating it successively and provide more and more details at each successive refinement. So basically, if you see, the concept of abstraction and refinement are actually complementary to each other. They're supporting each other. When abstraction enables the designer to specify procedure and data and suppress the details. In abstraction, we are saying hide the details, and in refinement, we are saying that you keep refining the higher level abstractions to lower level abstractions by providing more and more details, so that the designer is exposed to low level details as the design progresses. So slowly you give the details. Then comes the architecture. So what do you mean by the architecture? So software architecture suggests the overall structure of the software, how the structure provides the conceptually integrity for the system. That means as a together, when we take the whole system, integrated system, then it provides a concept for the system. That means it is not executable, but it is conceptually understood, that we can understand it as a whole, how it behaves. So different models to represent architecture are structural, framework, dynamic, process, and functional. So what happens basically in the architecture? We are defining the structure of the software, how the components are organized in it, and that and 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 the organization as a whole is providing as a system. So that concept, how it is working, that is called the architecture. So in structural, we provide the organization as a collection of components. In the framework, increase level of design abstraction by identifying repeatable architecture design framework. So we have said that the designing should be repeatable. So here what we try to do, like patterns, we also have architectural design frameworks. So we try to use those frameworks so that there can be increased level of design abstractions in the architecture. Then we have dynamic address the behavior of the program architecture and indicating how system or structure configuration may change as a function. So this provides the dynamic nature. It provides the dynamic nature, represents the dynamic nature. Then we have the process, which will focus on the design of business or technical process that the system must accommodate. So because we have functional requirements, business which deals with the business, or any technical process while we are implementing, we have to implement it, so we need to have technical processes of implementation like IO and searching, sorting, or any other thing, sending a message, things like that, synchronizing. So those are processes that we do, either technical processes or business processes. So the design has to take care. In the architecture, there has to be some aspect of the architecture has to take care of the process representation. Then we have the functional representation. So the functional representation has to form a hierarchy of the system. So when we go from the higher level abstraction to the lower level abstraction, In the lower level abstraction, we should be able to represent the functional part. That means its algorithms, its data structures, its steps, the instruction steps, or any calls or some things like that. Those have to be represented. Here we are talking of process. Here we are talking of function. Then we come to the next one, which is called patterns. Here design patterns are there. So we have to use those design patterns. So design patterns describe a design structure that solves a particular design problem within a specific context, and they are named accordingly. So over years, people have been doing software engineering practices, and they have been creating software. So what they have given a lot of patterns. What are patterns? Patterns are solutions to certain problems. So if you have you can define a particular problem context, a specific context of the problem, and if you in your software, if you encounter such a problem, then you have to go to the design patterns and find out, is there a already available design pattern for it. That means a way of solving that, a way of solving a particular problem. And if you have that, then you have to use those, because those are tested patterns, and people have got, just like architectural patterns, we have design patterns. So just to give you some example how what it is, we have a publish and subscribe pattern. Then there is a controller pattern. There's a model view separation pattern, and these are very much used. Where model view separation, where while writing an application, we try to view is our user interface context, and the model is our database, the data models. So this data model is normally separated from the user, so that we can have good security of the model. It will not get the data that is available with models, that will not get corrupted. So these are some of the, similarly to have a controller, when you have many a kind of sequence of activities, then you need a controller, and you have a dialogue, then you need a controller who will be doing the communication flow between the different parties. And similarly publish and subscribe. Then we come to the modularity concept. Modularity concept starts with the process of partitioning of the software into unique named and addressable components. The process of dividing the software into smaller and smaller and smaller components is called partitioning, and these components are called modular. So if you can make it modular, that is called what is known as modularity. Because these are called modules, therefore this process is called modularity. And these modular components should be able to integrate it to satisfy the problem requirement. So we have to partition in such a way that it will be partitioned into smaller components, but as a whole integrated system, it will solve the requirement. Architecture and design pattern embody modularity. So whenever we have some architecture patterns and also the design patterns, then they are normally taking care of the modularity. It makes use of a divide and conquer strategy. It is easier to solve a complex problem when you break it into manageable pieces. So you keep dividing and into smaller pieces so that you conquer the problem of managing large things, because managing smaller pieces are much easier. However, as the number of modules grow, then effort and cost will also grow. Because you have to manage more modules and you have to integrate more modules. So there is always somewhere you have to keep a balance between under modularity and over modularity. So that has to be determined very judiciously, so that the manageability is good, the partitioning is good, at the same time the cost is not very high. So what are the benefits of modularity? Development can be more easily planned because we have many modules, so we can do it in iterations, or we can do it in an evolutionary manner. Then software increments can be defined and delivered. That is what I was discussing. Changes can be more easily accommodated. because we can find out, we can debug and find out how many modules are being affected. So only those modules will be changed, not the whole software. And therefore, testing and debugging can be conducted more efficiently because everything is localized. And long-term maintenance is better because problems are localized and it will not affect the complete software. Then we come to the next concept of information hiding. So what is information hiding? So information hiding helps in deciding modular decisions. So when we do the modularity or we try to break the system or partition it into modules, then this information hiding principle is very helpful. It suggests design decisions regarding the modules. A module should be characterized by design decisions that hide it. And these can be procedural, processing, algorithms, and data structure. And it will be hidden from other modules. So that is the idea. And that if you do information hiding, it is good for modularity. You can also get independence. So hiding ensures modularity by defining set of independent modules. So dependency is less if you do information hiding. That communicate only when the information is necessary to satisfy the software function. So a module will work on its own independently only when there is a necessity for it to communicate to another module, then it will do it. And that will be under a proper manner with a particular interface in a controlled manner. So this is, we have already discussed this. It will be hidden in such a way that it is inaccessible to other modules. Only in a controlled way it will be accessible. It is not accessible freely. It is not accessible randomly, but in a very controlled manner. Only through the particular interfaces that is being exposed to the external entities. So what is the benefit of information hiding? Because the data and procedure are hiding from other parts of the software, when modifications are done during testing and maintenance, unintentional errors reintroduced are less. Sometimes it is when we do some errors fixing, we by mistake, unintentionally, we also change other parts. And we don't know that other parts will get affected. And it is difficult to test everything. It is difficult to debug everything. It is difficult to remember also everything. So if you have kept it in a hidden way, then it is so much protected that you cannot make the error. So only through the messages it can go. So unnecessary modules will not get affected. Then we come to the functional independence. So what is functional independence? It is an extension of the modularity concept and information hiding and abstraction. So abstraction says hide also says that you give only less information, you hide it. Information hiding says even more, you hide everything from the other modules. Abstraction says that you give it slowly. At a higher level, you have only overall, and then you keep refining it. And then you have the modularity, which says that you have to partition it into small modules. And then you come to the functional independence, which is using all these concepts, but it is extending it. And what it says, functional independence design in each module addresses a specific subfunction of the requirements with simple interface, avoiding excessive interaction with other modules. So this concept of taking the user function and dividing it into smaller and some smaller subfunction is the key behind functional independence. So if you do it in terms of these functions, then that module will automatically become independent. It will not have any, it can hide its information inside it. It can be abstracted, and it will provide only simple interfaces to interact with others. Concept takes the design decisions implying modularity, partitioning based on functionality. So the partitioning modularity is now based on the functionality. So you have a way to go for the modularity. Functional independence is very useful because it is easy to understand, develop, test, and maintain. The error propagation again is reduced by localizing the individual modules, as we have discussed in the other concepts. And moreover, because it is partitioned in terms of sub-functions, each module can be a reusable unit. So the reusability of the modules gets increased. So it is a way of implementing the modularity. You can say it's a way of implementing the modularity concept by using the functional independence. Then comes the concept of refactoring. We talked of refactoring when we were discussing the agile process models. So what is refactoring? It is a very important design concept. It is a technique of reorganizing the internal structure of the software to simplify the design. In architecture, we have said that we are giving the organization of the structure of the modules or the components of the software. And in refactoring, what we say that we are going to reorganize it. So the technique of reorganizing it, the internal structure, to simplify the design while keeping the software functionality and external behavior intact. See, whenever we are talking of refactoring, that means the design is already completed. In other concepts, we were doing the design, but when we do the refactoring, already design is there. So there is some architecture which is describing the structure, and we have to now reorganize the internal structure or refactor it. That means whatever factoring we had done, whatever decomposition we had done, now we are redoing it. What is our aim? Our aim is to simplify the design. So with the goal of simplifying the design, we will refactor it or repartition it or reorganize it. And when we do that, we have to keep in mind that the software functionality and its external behavior will not change. It will remain intact. That means the functioning of the software will not change. It will appear the same to the user. It will continuously be operable, but the internal structure of the way it is reorganized, the way it is partitioned, the modules, the module structure that we have got earlier will change. Or you can say in a very base implementation method, you can say if you have got the classes defined in certain way and the relations, then you are going to redesign your classes and its relations. Then it can be called as the refactoring. Refactoring, what is the focus? Focuses on problems in the software, such as unused design elements. So there could be initial design, there could be some element which is not used. So those can be removed. Then inefficient algorithms. That means the methods or the implementation of the operation in terms of methods are not proper, or maybe it is not in the right place because we have not defined the relations in the right way. Inappropriate data. When I say relations, I'm talking of the class relation, that is the associations, different type of associations. So if the class associations has changed, whatever we had designed over many maintenances, as and when we keep on doing maintenance on the software, they keep on changing. So the algorithms become inefficient. So that is what we have to take care during the refactoring. Then we have to see inappropriate data structures. So data structures which were considered to be appropriate at the beginning of the design when we created the software, later on is not being used or they are inappropriate. We can do a better data structure which will increase the efficiency and it will simplify the design. Then modules with low cohesion. So if there are some modules which have very random way of cohesion, then also we will have to do. Cohesion means the strength, the inner strength of the module. That means how loosely or tightly the internal parts of the module are related to each other. That is called cohesion. So we need to see that a module has got related parts. It doesn't have additional part which is not necessary to be inside it. So if that happens, then we say the module has a low cohesion. So if you have this kind of nature, this kind of modules having unused design elements, inefficient algorithms, inappropriate data structures, or low cohesion, then you can think of refactoring these so that your software will become more efficient and the design will be simplified. So we have come to the end of this lesson. So summarizing whatever we have discussed, we have looked at, we started with the design engineering concept, and then we brought it to the software design concept, the context of software design. And we also saw the design components, and we mapped it to the analysis models, because finally from the analysis models we have to derive these software design components. So we need to know which inputs we have to take from the analysis models and how we will go for the software design. We discussed the attributes of defining quality software, and from this we looked into the good design principles, and we said that these principles can be followed as a quality guideline for conducting our software design. Then we went over the fundamental concepts used in the software design that will ensure quality of the product in terms of the quality attributes. So now in the subsequent lessons, we will go into the specific areas of the design process, the 4 types of models that we have to create in the design process, and we will look into the detailed aspects of those 4 processes. So thank you very much for listening to me, and I hope this class is useful to you. Thank you all.